Hey everyone, I thought I'd make a little screencast for you about Lab 7S where we did our Moore titration, our chloride analysis based upon the potato chip filtrate that I had made for you. So let's start with just an overview of what we had in the mix. We relied upon two different reactions to be able to determine the chloride content of that sodium, of the salt containing potato chips. And the primary reaction that we relied upon was this reaction right here, where we see silver chloride precipitating out of solution when we add silver ions. So effectively taking this equation and pushing it to the left through the addition of silver ions, which we added through silver nitrate. And you notice the KSP for this process is very small, which is what we expect for insoluble salts. Now, our indicator in this lab was different than indicators in acid-base chemistry. We actually used a secondary precipitation reaction as an indicator that involved chromate ions. So once we had eliminated all of the chloride ions from solution, then the chromate ions could kick in and start to precipitate. And I'd like to show you how we know that this is true, because the KSP values are reasonably close to one another, and there's a different factor in terms of stoichiometry between the way silver ions are involved in the second indicator precipitation versus the primary silver reaction with chloride ion. So what you see here is just a quick little setup of what we would see on the nanoscale of our introductory solution. So just for clarity, the red dots, those are my sodium ions. These green ions are chloride ions. And these purple ions here are a simplified way of me to show you chromate ions. So these are our indicator particles. So notice we have presence of all of those in solution. And just for clarity, I'm not showing water molecules. Obviously, it was an aqueous solution. Water molecules are all over the place. So to understand what's happening, what we really need to do is do a little ice table and look at concentration of silver ions that would have to build up before you had a precipitate form. And to do that, we can use an ice table, and we've done this several times now, but when we look at a KSP situation, we're looking at the solid and its ability to dissolve in aqueous solution. And we know by now that we don't really need to consider this part of the ice table because it's a solid. We don't include solids in equilibrium expressions. So the idea that we have from the beginning is that initially we don't have any of this substance in solution. And we want to think about, well, what would happen? Some of this salt would dissolve if we were going to make a saturated solution of silver chloride. So it would increase by some amount X. We pay attention to the stoichiometry of the reaction. It's all 1-to-1. And we have equilibrium concentrations in that saturated solution of X and X. And then from there, we can plug values in to our KSP expression, which would just be Ag plus times the product of Cl minus. Both of these raised to the first power because their coefficients in the balanced net ionic equation here are 1 as well. And we plug in our values, and then that's just X times X. And our KSP is essentially equal to X squared. You take the square root of KSP, and you'll get the value that you see right here. So what this means to us is, before this precipitate, silver chloride, can even form, we have to build up a silver ion concentration of at least 1.3 times 10 to the minus fifth. Once that concentration has been exceeded, then what happens in the process is we start to see a shift over to the left. And you can think of this as a Q versus K analysis, because until we get silver ion concentrations equal to or greater than 1.3 times 10 to the minus fifth, Q is either equal to K or less than K. And in that case, no reaction is going to happen. Once Q gets greater than K, then we see this shift to the left and a precipitate forming. If we do the same analysis, so remember this number, 1.3 times 10 to the minus fifth, we do the same analysis now for silver chromate. And what we'll see is a slightly different value, which I don't think will be surprising. So if we imagine making a silver chromate saturated solution, we would start with silver chromate, put it in some water, and let it come to equilibrium. Now, the things we need to pay attention to are the differences in the stoichiometric proportions in this particular reaction. So again, we're going to make this assumption that we don't really need to concern ourselves with this portion of the equation. And initially, there is no ions of silver and no ions of chromate in solution. Now, if we think about our change, we know that some ions are going to form. Some amount X of silver chromate is going to form. Now, here's where we have to look at coefficients. For every one silver chromate formula unit, we get one chromate ion. So that would be plus X. For silver ion, it's different. It's twice as much. So it would be plus 2X. So then at equilibrium, our equilibrium amounts would be 2X and X respectively. So when we plug these into our KSP, we also need to be careful about writing our KSP expression appropriately. It's going to be silver ions concentration squared because there's a coefficient of 2 in the balanced net ionic equation. And for chromate, it's just to the first power. So when we plug in our values here, we get 2X quantity squared times X, which is 4X cubed. And then we can solve for X, and once we solve for X, we will see that we get a value here. And notice how this concentration is larger. It's a full order of 10 larger concentration. This is the whole reason why silver chromate doesn't precipitate first. It doesn't precipitate because it needs a higher silver ion concentration in order for that precipitate to form. So if you have both possibilities, and we do because in our solution, we start out with a solution that contains substantial amounts of chloride ion, then that situation is going to favor the precipitation of silver chloride first. But then after the chloride ion has all been removed, then we can start to precipitate the silver chromate. And we can see that here just in summation of looking at these things. And the key thing I'd like you to remember is you can't just look at these KSP values and do a direct comparison when you have different ratios of those ions that you're adding into solution. You really have to do a more thorough analysis. And the analysis that we did was just looking at what the tolerance level is for concentration of silver plus ions in saturated solutions of our solution. Okay, this is actually wrong. We should cross it out. So if we look at its concentration of silver ions in saturated solutions of their respective salts, and we see that for what I've color-coded here in green, this is the green equation here. So for that, in that situation, silver ion, there's a much lower tolerance for silver before a precipitate will form. And this is for the silver chloride. And then for our indicator, this is where we see a secondary precipitation because you first have to remove all of the chloride. And then once you've removed all the chloride, then you can start to have a reaction with chromate with any additional silver ions that you add from your burette. Hope this was helpful. Now's a good time to kind of talk with your group members and get started with the analyzing questions from Lab Activity 7S.